Hi, everybody. Welcome. Hope everyone's doing good in the RWAi XDC dev sprint here. Today, we're really excited to have Quex joining us. We have Vasily and Alexander. And yeah, we're going to be getting into TEEs, trusted execution environments, just a lot of topics that I know I'm personally really interested in, so I'm sure a lot of you are as well. That being said, I'll hand it over to you guys if you want to introduce yourself.
All right, Alexander, go ahead.
Okay, my name is Alexander. So I'm a developer in Quex, mostly responsible for developing smart contracts. Yeah, I think it's main part. Vasily?
Right. I'm Vasily. I'm currently CTO in Quex, so pretty much doing infrastructure and architecture for our system. So that's it.
Great. Awesome. Do we want to just go ahead into the presentation?
I think so.
Okay,
so
awesome.
let me start. So our presentation today and our talk today will consist of two parts. So as a first part, I will introduce you to the basic concept of Quex, very, very basics of our architecture and why we use T, what are we capable of. And then I'll pass the word to Alexander, our co-developer, who will show you how to actually use it and provide you some hands-on experience on the details of on-chain interaction with Quex. So the goal of today's presentation is not actually to get into very technical details of all the functioning. In the end of the day, during the hackathon, you will be mostly interested in how to use it. And so for the first, take the first part as a very, very brief introduction to the topic, because of course the topic of TE itself is very diverse. So take the simplifications I will make with a grain of salt. So first, what is Quex? Quex is a TE-based data transfer layer for the Web3 solution. I'll talk about TE a bit later, but what do we mean about data transfer layer? So if you do smart contracts, normally you operate with the data which exists in the context of the blockchain, but there is somebody who put it there. So by design, from the very start, those side effects of transferring data to the blockchain was what actual other users do. But now, when the infrastructure evolves, you probably know of plenty of Oracle projects around there, and their goal is actually to eliminate the trust of the intermediary between the outer world and the blockchain. So in case you want some data which doesn't exist in the context of the blockchain yet, you need somebody to transfer it on chain. And in some cases, you need to trust the actual person who posted the transaction containing the necessary data. In some cases where you have some separate consensus and decentralized data transfers, you rely on the consensus among several nodes. With Quex, we leverage the trusted execution environment technology to move the trust from the relaying party to actual hardware vendor. Because these days we can have special hardware with this secure execution, so that you actually do not need to trust the hoster or hypervisor or operating system which is in charge of running the software you deployed. So that's what we are doing. In a very narrow sense, the Quex can be treated as oracles. But if you take any oracle which relays some external data on chain, the relay process actually consists of two parts. First, you fetch the external data. The second part is you somehow post-process the external data, because it's quite rarely that the endpoint you're achieving is providing the data in the correct format, in the exact format you need. So what you actually have inside is some code, some routines which are post-processing this data, and with TE abstraction, it's quite straightforward to elevate this idea and say, well, okay, I can do some simplistic post-processing, but what actually stops me from deploying some sophisticated code, such as, let's say, LLM or some involved database on that layer? So, for example, you want your own coprocessor, so you have some logic, and this logic is too heavy to be deployed in a smart contract. You'll simply run out of gas when running it. For that purpose, potentially you can construct your code in some normal programming language and deploy it inside trusted execution environment. And that hardware security guarantees will prevent the attacker and even you from interfering with the code execution flow, and you will be able to trust the results. So you, in a sense, you also get an oracle, but the oracle which just does code processing without necessarily fetching something external. So that's what Quex is. So let me talk briefly about TE. TE stands for Trusted Execution Environment. In very basic terms, these are hardware guarantees of execution flow integrity and execution correctness. Imagine the situation that you're running some code on a server. Once you have, let's say, root privileges or hypervisor privileges on the server, normally you can post that process, manually dump the volatile memory, analyze it, extract the secrets which were contained in the code, or even manually change the state of the registers of the post processed, or change the state of the memory, change the instructions, then start trying again, and you'll be fine with that. Well, TE is exactly what prevents that pattern of behavior. These are the mechanisms that prevent someone with physical or hypervisor access to the host from changing or reading the process memory. And during the recent times, the technology has evolved to the state where the abstraction you work with is not necessarily the process, but it can also be a virtual machine. So you can run a virtual machine in the encrypted memory region. That memory region will be encrypted with a hardware key. And that hardware key is actually the thing which belongs to the CPU itself and fused into during the production stage. So that hardware key never leaves the CPU itself, and the execution flow is separated from the general execution flow. So once you dump the memory, you get just a chunk of encrypted data. And if you have the integrity control on that memory, you cannot even change it in any way so that CPU doesn't detect what you're doing there. For the second part, you will be interested in, okay, I'm running some code in the secure execution environment, but how can I trust that the data which I'm getting out, because the data out of the trusted execution environment is obviously stored in normal RAM, not in some heavily encrypted region. How can you make sure that this data comes from that process indeed? And for that, the vendors normally introduce the procedure which is called attestation. So actually, the hardware chips are capable of presenting the data structures containing the information about the actual process or virtual machine which is running inside, namely the hashes of instantiation process and the state of some registers responsible for the trusted code execution. And this structure is signed, well, to simplify a bit, we can indirectly say that it is signed with a hardware key. And you know the public key counterpart, and you have the certificate chain which goes back to the vendor and certificate authority. So, and you can put some customer user data. Your process can put some user data inside that attestation, so that virtually user data is signed with the chain of keys, which is traced back to the root certificate authority, which is published by the vendor. So you can reproduce the hash of your virtual machine build, or you reproduce the hash of your process build, depending on the technology you're working with, and verify that the data is indeed authentic. In Quex, we rely on Intel Trust domain extensions, relatively new technology, which is designed by Intel exactly to run hardware-protected virtual machines on Intel server CPUs. Here is a small schema. Again, take it with a grain of salt to get an impression on what happens there. So we see the CPU which communicates with an encrypted region in RAM. That RAM is encrypted with a hardware key. The execution flow inside of CPU is execution pipeline is separated from the general execution pipeline. Whenever your process or your VM, whenever your hypervisor switches contexts, the RAM is dumped as an encrypted chunk, and the hardware key never leaves the CPU, so nobody ever knows it. And in order to verify that it is the virtual machine you were intended to run, you can request an attestation report from the CPU, which will be signed by effectively by the hardware key, and sent somewhere else, let's say to the hypervisor. So how to sum up, let me tell you just the steps we want to take to make it work. So we can instantiate the virtual machine, which privately generates the key pair for further use, because you cannot use the hardware key for that purpose. These virtual machines sends the public key in the attestation report, and this public key together with attestation report can be verified on-chain on Quex smart contracts, so that we register the trust domain. The trust domain is Intel's terminology for the virtual machine in TDX, so that we know that this virtual machine runs in TDX indeed, and it possesses this exact public and private key pair. We have vendor guarantees that nobody knows the newly generated private key part. You can verify it by comparing the hashes in the attestation report with the hashes you expect from the VM instantiation, and you create the VM in a specific way so that it doesn't have SSH, it doesn't have console, it doesn't have any devices except that, let's say, the network adapter and the simple web server hanging on that network adapter. So you cannot log in there even if you're a developer of that machine. And after performing this comparison, you can verify that this VM indeed does what it claims to do. And after that, we register the public key owned by the virtual machine in our Quex contracts, and we can claim that every piece of data which was signed with the corresponding private key comes from the virtual machine which it was intended to, and we have hardware guarantees for that. What does it mean for us? For us, it means that first we can deploy arbitrary processing logic inside the virtual machine, and we don't need any special recompilation procedures for that. So generic software will run quite well. Second, you don't have extra consensus layer. So you have instead of consensus-based oracles or consensus-based coprocessors, we have hardware vendors security guarantees. So you can relay the data relatively fast and cheap. As a very simple example, I can tell a bit about the HTTPS Oracle, which we have deployed on XDC as well. So here is an overview on how Quex works. So in the right bottom corner, you can see the data consumer contracts. It's probably it can be some DeFi application or prediction market or anything which needs some data or co-processing, which is too heavy to be put on chain otherwise, or just needs connection to the outer world. For example, it can be some reader of the price feeds or some bridge and token contract, whatever. It can access the Quex core and Oracle contracts and create the request for the data there. The Quex core and Oracle's contracts register that request, assuming that the corresponding virtual machine is already there, and emit some event which gets caught by the relaying service, because you don't want your relay to reside inside the trusted execution environment. Well, normally your relayer just passes the signed messages back and forth, and the worst it can do is just can refuse to pass the message. It cannot force signatures if the cryptography you use is actual cryptography. The relaying service knocks to the trust domain, the virtual machine we are running, and the trust domain makes requests to external REST API. Let's say the API of CoinMarketCap, or API of ChatGPT if you need some responses from ChatGPT on chain. After that, it received the response, makes post-processing for that. Alexander will go into more detail about this. Returns the signed data, which is already post-processed and formatted to fit into the blockchain we are using. So here we are EVM compatible, so we use ABI encoding. And relaying service returns it to our core contracts, and in the end here, data consumer contract received the data, and once it goes from the Quex contract, it can you can actually trust that the data is authentic, and we haven't changed a single bit of it. So the actual magic is happening inside the trust domain, because how can we know that we are accessing the right REST API? Well, we check the TLS certificates for that and do all the TLS verification inside, together with certificate transparency and timestamping. So you don't need that logic on chain. But all you need to know to use all that visually long machinery, all you need to know is actually the part of connecting the data consumer contracts with the Quex core and Oracle contracts. And in order to, and the Alexander will show you how exactly to do that, how to use it, and I hope he'll show some nice live coding. Thank you.
Thanks, Vasily.
If you want to just share your screen, Alexander, and we can.
No. Firstly, I want to continue presentation. Then
Okay.
moment. Yeah, thank you. So where I can switch slide.
It's right on the same window. So where you see that slide.
Okay.
If you hover over the slides, you get little arrows. But I can cue it for you if.
Okay, it would be nice because I don't see it here. Sorry.
Okay, yeah, totally. Just let me know and I'll go through them for you.
Okay, thank you. Next slide, please. Okay. So previously, Vasily told words, Quex, Core, and Oracles. And first of all, I want to tell about some high-level helicopter view on our solution. So it could be seen as a two-layer solution. So first of all, it's application layer and infrastructure layer. On infrastructure, on application layer, it consists of Oracle pools and trust domains. So about trust domains, Vasil told a lot. I won't repeat him. But for what this layer is responsible for? It's responsible for defining specific tasks. So as Vasily said, that we can run on this infrastructure various different oracles. So for example, data feeds, HTTPS requests we have right now, or you can put some neural network inside trust domain and create requests for this trust domain. So application layer responsible for defining specific tasks, defining contracts to interact with this trust domain, and trust domain actually perform this task. So on infrastructure layer, once again, Vasily told about trust domain extensions, Intel's technology, but on chain part, we have Quex core, which is responsible for storing all data, all data related to attestation reports, all certificates, certificate chain. So what else? Yeah, and this part also responsible for verification of responses, signed responses from trust domain, and deliver it to user's contract. So let's move next. Austin, could you please? So let's talk a little bit about application layer. So as I said, this layer responsible for defining particular task that this Oracle pool and trust domains performing. At Oracle pool is on-chain part of this layer. It manages all actions that users created, provides access and providing access to these actions, and allow user to provide user an interface for action creation. Also, Oracle pool implements trust domain policy, so it could this part authorize if particular trust domain can perform action for this Oracle pool, and it could be implemented based, hardware parameters, some hardware specification, virtual machine image, or could be just an allow list of trust domains. And also at this level, we trust domain and Oracle pool must establish some common protocol for interactions. So trust domain should understand byte representation of the action Oracle pool provides. So, and serialize its own response in understandable for user format. Let's move next. Thank you. Okay. It's just an example of an action. On the slide, you can see just an example of an action of our current Oracle HTTP request Oracle pool we provide. You can see it consists of requests divided into two parts, public parts and some private parts for some APIs, for examples. It also consists of, it also includes GQ filter. It's JSON transformer filter and specify response scheme. Yeah, let's move next. We will see it in action a little bit later. On infrastructure layer, we have, once again, we have trust execution environment, and on chain we have Quex core. I focus only on Quex core because about TE is really told a lot. This layer, on-chain part of this layer, responsible for registration and maintaining trust domain information on blockchain. So it stores all report data from trust domain attestation, from about its parent certificates. So you can think about this part as digital identity system that maintains the full chain of trust. So we have all information from Intel's root certificate to individual trusted domains information. Also, on this level, we have data flows. About this, I will tell a little bit later, but it's some combination of action we want to perform and where to deliver result. And probably the most crucial part of this Quex core part, it's verification of trust domain responses, verification of signature, freshness of data, and all other stuff. Also checking that trust domain is allowed to perform this particular action. Let's move further. Thanks. So about flow, I mentioned on the previous slide. Flow is a routing abstraction that specifies which action an Oracle pool needs to execute and how to deliver its result to a customer contract. The action part tell us which Oracle pool to use and which specific action to execute. the callback part defines how to get the results back to the customer contract that requested the data. And also it allows to limit gas on users' callback to prevent some huge gas spending. So let's move next. The next part. It's, right now I share my screen. 1 moment. For this demo project, I decided to take prediction market implementation. So we have some prediction for, let's say, Bitcoin price at the end of the month, for example, or any other token. Let's briefly review what we have at the beginning. So we have some markets. So our prediction market contract supports multiple markets at the same time. We can create new market, providing description, target price, month, start timestamp, and token pair. We providing some ability to read information about this market, some place prediction for market users, claiming price, some zero fee, some working with fees, and the most crucial part, we want to resolve market, where it's the part where we need to get some data from, in our case, we will say from Binance. So we want to close our prediction market, and for this, for getting information, for getting final results of what was the highest price of particular token pair during these months, we need to perform request to Binance. Request looks like this. So we go into get clients or candlesticks from Binance for particular token, from particular timestamp. It's beginning of this month, interval 1 month, and we need just one candlestick to perform our request. Response will be in format like this. We have an array of candlesticks. Each candlestick looks like this. It's also an array.
Is that what Binance returns, right?
Yes. It's Binance response. So we need third element of this array, its highest price during this candlestick. So we're asking for monthly candlestick, so it would be highest price during the month. So
wait, and that function takes market ID as an argument. Does it consume that final number or no? So you're going to fetch the result on Binance.
Yes.
Take the one field that that highest price on the
Yes.
month candlestick and put it back on chain. And where do
Yes.
you transfer it? Where's the callback on the contract?
We will implement it right now.
Oh, cool. All right.
So yeah, we have our start point. So we need to resolve our markets to get our price, highest price of particular token during the month. So first of all, we need to install Quex interfaces. Let's start with this. So forge install. Quex. So I already installed it, just not to waste our time here. Let's. So first of all, what we need to create action and create flow based on this action. Let's start with this.
Once again, action is something that Oracle performs. In our case, it's the request, right? HTTPS.
Yes, in our case, it will be a HTTP request that I showed before. Okay, so let's write a function. Create Quex flow, for example. We need for this function token pair. And we need timestamp. Oh, okay, it's already suggested. So so we need to create HTTP request, create our action. First of all, let's import our interfaces. Wait a moment. I have again. Just so we need a few interfaces to interact with our Oracle pool. Request Oracle pool interface to create action and specify our action. We need Quex action registry to create request and flow registry to create flow.
Once again, the flow is the delivery mode, right? So it's actually pointer to your callback in a sense.
It's a combination of action and callback.
Right.
Yes. Let's. So we need to add them to construct them. No. So we need addresses of Quex core and Oracle pool. And we need to create interfaces to interact with it. Oracle pool. So we have Oracle pool, action registry, and flow registry. Let's create them in constructor. Yeah. So we create an Oracle pool. with Oracle pool address and Quex action registry with Quex core address and flow registry with Quex core address. So first of all, let's create an action. We need Quex action registry, create action. For this, we have, you want to ask something? Okay. For this, we need to create HTTP request.
So you are registering your custom request with Quex so that it knows what to query from the TD, right?
Yes. Okay. As I told, HTTP request action consists of few parts. Let's create first one. It will be HTTP request memory HTTP request. It consists of the following parts. HTTP request consists of method. So we specify that it's a get method. We need to provide host. It would be at Binance.com. So, we need to provide path to path of our HTTP request. It's at the v3 coins. We need to specify headers. In our case, we don't need any headers. Sorry. Request header. We don't need any of them. So we need to specify parameters. Query parameters. So we need how many of them? 1, 2, 3, 4. We need 4 query parameters and body. In our case, we don't need body. So let's add our query parameters. Okay. So we need symbol and it's talking pair. Okay. Perfect. Okay. Thanks. We need strings to string and Binance receive timestamp in milliseconds, so we have to multiply our timestamp with 1000. So what we done for now, we specify our HTTP request. It's a GET request for API Binance.com. Perform requests to take candlesticks. with 4 parameters: our token pair, start time for receiving data, interval 1 month, and limit to we set to 1. Also, we need to specify HTTP private patch. Let's do it. Oh, HTTP.
So private patch is an encrypted structure which is designated to store in API keys or private data so that you don't show the plain text on chain, right?
Yeah.
And here it can be empty as far as I understand it,
Yes.
because we are querying the open part of the API.
Yes. So in our particular case, we don't need any encrypted data to perform requests, no API keys, no other sensitive information. So we just create an empty patch. So it will be, we don't need any the path, we don't need any headers. We don't need any parameters. We don't need body. And in case if we have some private encrypted data, we need to specify which trust domain can perform this data, can decrypt this data to perform request. In our case, we would specify it just set to 0. It's our empty private patch. So, for example, if we need to add some API key to headers, we set request header patch with API key and encrypted API key with encrypted by using public key of trust domain we choose. If you need it, you can find public key of existing trust domain in documentation. Quex. So yeah, we specified. Yeah. Next part we have to specify its GQ filter and response schema. So let's start with. Okay. So response scheme. What we need here, it will be just integer unsigned int. So we expect that our result will be in this format.
So guys, the trust domain will format the response so that you can fetch it on chain and unpack in any structure you prefer. So you need to specify the type of the result you expect. So far we specify it as in plain string, but we hope the standard will be there at some point. So we'll have nice encoding for typing.
Yeah, and so we expect to get back from Quex only integer, but as you may remember, Binance return more complex structure. So we need to write GQ filter to extract data we need from this structure. So first of all, we need to get first element of an array. In GQ, you can write it in this way. So current object and then get elements with index 0. Result of this will be this array. From that array, we need third element, so index 2. Binance return this data as string, so we need to transform this data to number. For this purpose, we can use GQ function to number, and then we can multiply this number for some number. Let's say for billion. And let's round it for example, to get integer value as a result. So yeah, we created our action. As a result, we will get action ID. Then we need to create. So we created our action, got action ID. Then we need to create flow. First of all, let's define flow structure. We need to provide action ID that we created right now. We need to specify in which pool this action defined. For this, we need take an address from request oracle pool. We need to specify consumer. It's our contract. We need to specify callback. For this, let's define our callback function. For example, something like this. It should take request ID, that item, and ID type. I will explain ID type, all the structure a little bit later. So callback will be this Quex callback selector, and we need to specify gas limit. let's say some 500,000. Let's say 500,000 would be enough. So for now, choosing gas limit more precisely makes sense because it's part of request cost. In near future, we change it a little bit, and we will refund all unused gas made by callback. So it would be easy just specify some number that's more than enough for performing callback call, which is suitable for your economy, for example. So we defined callback. Let's create it. Register create flow. Yeah.
So good thing is that bureaucracy has to be done only once, right? So you know your request, you have to describe it once, fire that transaction exactly once, register the flow, so state your delivery address, and after that you won't need it.
Okay, yeah. About flow, about action, it depends. If you need perform multiple requests for one endpoint with all the same parameters, yeah, you can create action and flow only once, and then use your flow ID multiple times. In our case, we have different markets, and for each market, we need to perform request only once. So we need to create. I choose this example to show that it's also possible way to use Quex query. Yeah, but in our case right now, we will have to create action and flow every time for every market. But for every market, we need it only once. Yeah, but in general, some parts of request could be reused. Action could be created in two different ways. Right now, we created it by defining all fields at once. It's also possible to do it by parts separately, HTTP request, separately patch, separately GQ, and then combine it into one action. You can see it if you need in contracts in detail and in documentation. So here we created flow for retrieving our data. Yeah, here not request method, not method, request method. Yeah, so we specify all parts we need to perform this request. Let's create. Let's call this function here. Okay. Turns. Okay. So should be internal. Okay, we created flow. So next part, we need to perform request itself. We need to ask for data. First of all, let's get request price. Request fees consist of two parts. Fees for performing this request and gas fees for us from this request. Okay. So, and we need to create request. No. Sorry. Section registry, no. Create request. So final price of the request will be native fee plus gas fee multiplied by current gas price. So yeah. So we create our request. We can go to. So we run out of time probably. So let me briefly. Let's store requests. Let's create mapping from request ID to market ID. To market ID. Okay, and store our. We need this data because when we receive callback, we only have request ID, and we need some context to understand to which market this request ID, for which market this request ID return data. So yeah, let's retrieve markets. Sounds good. Yeah. At the end, we no, not that item. We have to decode our value. So we can do it this way and save to our markets our final price. Yeah, probably that's it.
Do you need to verify the origin of the call?
Yeah, sure. So we want to check that message sender of this callback is Quex core. Message sender, not historical pool. Section registry, yeah, something like this. Okay. If we have a few more minutes, I can show it's in action, but I think we already run out of time. but it's complete example. It's possible to run it.
Austin, do we have like 2 more minutes to run the example, or we are out of time already?
Oh, no, go ahead, run it. Yeah.
Okay, thank you. So let's deploy our contract. Okay, one moment. Forget to, I'd say it's in the last moment to multiply it by some number. So I wrote in advance some scripts to deploy, to get some, to create market to, okay. One moment. Not for registration. Quex action register. Yeah. Oops. Okay. Add action. No. Yeah. HTTP action. No, not request action. No. Request oracle pool. Should be request oracle pool. Decode. Oh. Sure. Data item. Okay, yeah. I forget to Quex Oracle register to deploy.
So you need to pass the addresses to the constructor, right?
Yes. I thought it would be a bit quicker and decided to prepare all. Okay, we have our contract. Let's save it to environment variables. Let's create market. Moment. Yeah, sure. Yes. Okay. What price should be?
They maybe have pre-deployed contract for that. That's in live coding. It's normal that.
Yeah, I have. Let's 1 moment. Okay. Something wrong with the script, probably. I don't see it now. Okay, let me open source that I'm sure that works. Instead of trying to fix it now.
But to sum up, the course of actions is the following. You need to register the actions where you describe HTTP request to the full utilization. You describe the type you want to be returned to your contract. You describe the post-processing script, which is written in JQ language. Somebody of you may be familiar with it, because it's quite neat for the post-processing of JSON data. And that script should return the mixed type array, which is mapped to the solidity structure inside the TD. And after you've done it, you register the request on the Quex smart contract oracles, and all you need to do is pull the create request function, right, for that, and wait for the data to be on your callback. Oh, obviously there is some there are some bugs right now. Sorry for that.
Yeah.
In live coding sessions all the time. Well, quite unfortunate. That's it. But so we have that HTTP oracles, and please refer to the documentation if you're interested. Don't hesitate to contact us if you need it. And if you need some custom post-processing, let's say AI or something beyond the HTTPS requests or some co-processor, please just contact us. You can run your own TDs and register them with Quex, and everything will work fine. But we can also at least try to help if you have some meaningful case.
All right, awesome. And I think anybody who's ever had to do live coding before knows that it will surface every bug that possibly can exist.
Yeah,
There's nothing like doing code on the spot. But no, absolutely. I mean, awesome product, guys. Super interesting with I mean, applications that go outside of Web3. So fantastic work. For anybody who is already in the XDC RWAi dev sprint, if you have questions, just ping an admin in the Telegram group and we'll make sure we get that question to the right person. If you aren't in it and you're interested in joining into the dev sprint, here is the URL to do that, where you can register in if this seems interesting to you and surface some like cool ideas for you. Or even if you have a different idea and are like, this kind of sounds interesting, make sure you go to that URL down there, register, and throw your hat in the ring. Other than that, though, thanks so much for showing us Quex, guys. Super, super interesting. Let me just check real quick. Okay, it looks like we're good. Yeah, thank you so much.
Thank you, Austin.
Thank you.
Thanks
for having
everybody
us.
who joined.
All right. Thank you everybody for watching. And we'll see you in the next workshop. Bye, everyone.
Thank you.
Bye.
Bye.